Mr. Watson here, and in this video we're going to be looking at heart rate, stroke volume and cardiac output. So, why are we interested in these? Well, we're interested in them because we're looking to assess the efficiency of the individual's cardiac muscle, that myocardium we were speaking about in the last video, as it links to aerobic performance, okay, how efficient someone's heart is, how efficient someone's cardiovascular endurance is, okay. So, as we know, the heart dual pumping blood around the body, and we have heart rate, okay, and we should know 0.8 seconds at rest, one cardiac cycle, which would represent one beat, and heart rate is beats per minute. And on the other side, we have stroke volume, the amount of blood that is ejected from the left ventricle per beat, and that's measured in milliliters. We'll go into this in more detail in a moment. That's what we have. And the interaction of these two give us cardiac output, which is measured in litres per minute, and that's the amount of blood that's ejected from the left ventricle per minute. Okay, so let's take a closer look at these, starting with heart rate. So like I've already said, heart rate is the number of times the heart beats per minute, okay, BPM. The actual units of it tells you the definition, beats per minute, okay? So an average resting heart rate is around 72 beats per minute, or 70 to 72 beats per minute is the average resting heart rate. For average individuals as well, I should say. We're not talking about elite athletes here. Now, this is a general rule. It's not always the case, but it is a rule that we can kind of go with, and it's the lower the resting heart rate, the more efficient the cardiac muscle. And that's why we'll often hear about terms such as aiming for bradycardia, which is a resting heart rate below 60 beats per minute. Okay, so it's quite a low resting heart rate, and that's known as bradycardia. Okay, so what it suggests is that if you have that, when you go into exercise, your heart rate takes longer to get to its maximum, and we can maximize stroke volume. But again, we'll go into it in a little moment. What causes bradycardia? Well, we have something called cardiac hypertrophy, and this is deemed to be the reason for bradycardia. We have an increase in the size of the cardiac muscle, and it becomes stronger and more efficient. Okay. Now here's a little example of the twins, the Brownlee twins, and this is Alistair Brownlee's resting heart rate. He was recorded at 34 beats per minute, which is, wow, I mean, very efficient heart rate. Okay, triathlete, strong cardiac muscle, probably has a lot of, or experienced a lot of cardiac hypertrophy through all of his training, and as a result has a very low resting heart rate. And a heart rate maximum 220 minus age. Should know that one from GCSE. Okay, I should probably also mention that someone's resting heart rate is affected by genetics, gender, but largely fitness can affect this. Okay, and we'd definitely be expecting other elite athletes like the Brownlee twins to have bradycardia. Okay, so that's heart rate. Stroke volume. So stroke volume is the volume of blood ejected from the left ventricle per beat. Per beat being key, not per minute, because that's cardiac output. It's per beat. And that's measured in milliliters. Okay? Now this occurs during ventricular systole. Okay, as the ventricle walls contract, the blood is ejected into the aorta, as we know from the cardiac cycle and the pathway of blood in the last video. Okay? So it occurs during ventricular systole, the left ventricle we're interested in, so I've cut that in half there. And an average resting stroke volume is 70 milliliters. And again, this can reach much higher values in trained athletes. Okay. Now, just to go a little bit deeper with this, stroke volume is dependent on two factors. And one, as you can see there on the screen, is venous return, the volume of blood returning to the heart. Okay? So venous return is the volume of blood returning to the heart. And what we can say is, the greater the return of blood, the greater the volume of blood to eject. So basically, the more blood that's returning, okay, so the body to the lungs, back to the heart, and essentially once it goes on its pathway, the more blood we have coming back, the more the left ventricle has to contract and push out. Okay, so it makes sense. If you have more of it, you can eject more. Okay? Now, the second thing is ventricular elasticity and contractility. And what this is, it's the degree of stretch in the cardiac muscle fibers. Okay? And what we can say about this is, the greater the stretch, the greater the force of contraction, the higher the stroke volume. So that can sound really complicated, elasticity, contractility, venous return, but think about it. If more blood is coming back to the heart, okay, it's going to fill up the left ventricle. But if there's a stretch in the walls of the cardiac muscle of the left ventricle, okay, and that can stretch bigger, it can fill with more blood, and it's good, as we know, it goes from high pressure to low pressure. And if you're creating higher pressure from simply having more blood in there, well, the force of contraction is also going to be greater, and you'll have a higher stroke volume. You will eject more blood per beat if you have more blood to eject, and you have greater elasticity and greater force of contraction in the left ventricle. Now, this is partly due to an increased ejection fraction. So we've got another term there. But it's not a term, again, we need to panic about. We can break this down simply. Now, ejection fraction, okay, there's a reminder of what stroke volume is. But ejection fraction is the percentage of blood ejected from the ventricle, and the left ventricle. So what this suggests is, if we have a percentage of blood that's ejected, that means if it's not 100, there's going to be some blood left in there. Okay? So we're looking at what is ejected out. So let's take a look at it. Ejection fraction equals stroke volume. So we know stroke volume is the volume that's ejected from the left ventricle per beat, divided by end diastolic volume. Now, all that means is, what volume of blood do you have in the left ventricle or the right ventricle at the end of the diastole phase? Okay? And what is ejected is going to be a percentage. So what it's suggesting is that, and it's true, we don't eject all of the blood out. In fact, at rest, 40% remains. We only eject 60% into the aorta from the left ventricle. 60% is ejected. 40% of blood remains. Okay. Now this does rise during exercise, but that's quite a lot of blood left in there. So how we would figure that out? We know stroke volume at rest is 70 milliliters on average, divided by around about 120 milliliters end diastolic volume. And that will give you around 60% of blood ejected into the aorta from the left ventricle. Okay, so as you can see, 40%. Now, what we're doing is we're trying to increase this percentage, increase ejection fraction, because that links to the venous return and the elasticity. Okay, And there's something we should know about called Starling's law. Okay, and Starling's law links all of this together. So let's go back to venous return. And I want you, while I'm going through this, to think about a balloon. Okay, so venous return. Venous return increases during exercise. So we know that's the volume of the blood returning to the heart. Okay, so if we think about blowing air into a balloon, okay, we're going to blow more air into the balloon. And what happens then is, as we have an increased venous return, it leads to an increase end diastolic volume. And you've just seen that in the ejection fraction formula. Because if we've got more blood back, then in the diastolic phase, we have more in. And if we're blowing air into a balloon and we keep blowing more and more, we have an increased amount of air in that balloon. Okay? Ventricular elasticity. So venous return increases during exercise. Increased venous return gives us an increased EDV, end diastolic volume. Increased EDV leads to a greater stretch on the ventricle walls. If you think of a balloon, once more air goes in and in, the balloon grows in size, and you put a greater stretch on the walls, almost like you're worried it might pop. However, what happens is, when you let go of that balloon, it's got a lot more air and it's a lot more forceful releasing that air. And you often see the balloon shoot up in the air. But what this means for us is, this greater stretch leads to an increased force of the ventricular contraction. So as you can imagine, if the ventricles have more blood in there, we need to try and eject it all out at high pressure into the aorta, okay? So this increased EDV leads to a greater stretch, and this greater stretch, like I've just given you with the balloon analogy, it increases that force of ventricular contraction. It has a much more forceful push, okay, which will lead to stroke volume. That greater force of contraction leads to a larger push or ejection of blood from the ventricles, okay? And this is Starling's law. So you can see how ejection fraction's tied in there, because the venous return has increased the end diastolic volume. And if we're dividing stroke volume by end diastolic volume, okay, the bigger that end diastolic volume is and the bigger the elasticity and contractility is, we can increase that stroke volume number and we get a higher percentage. Okay, so this is Starling's law. Okay, cardiac output. Cardiac output, the volume of blood ejected from the ventricle per minute, litres per minute. Now, if you remember from the first slide, I told you cardiac output is an interaction of heart rate and stroke volume. Okay, so from the heart rate it gets per minute, but from stroke volume it's interested in the volume of blood being ejected from the left ventricle. An average resting cardiac output is 5,000 millilitres per minute. And we're going to put that into litres in a moment, because that's how cardiac output is measured. But 5,000 millilitres per minute. Here's the relationship that I've just spoken about, that interaction. Heart rate times stroke volume equals cardiac output in litres per minute. So HR times SV equals Q. Okay. 72, as we know, is the average resting heart rate, times 70 millilitres in stroke volume gives us around 5,000 litres per minute. I think it's 5,040. Okay, so it's quite easy there to see the relationship. We just multiply heart rate by stroke volume, and that gives us our cardiac output. It gives us the volume of blood that our heart ejects from the left ventricle per minute in litres per minute. Okay. Now, what we're going to look at here is trained versus untrained. Now, as I said, athletes usually have bradycardia. Now, what it is interesting to know there, and I'll show you here, untrained versus trained. So heart rate 70 to 72, the range on average. In train, we've gone 50 beats per minute. Okay, 50 beats per minute for a trained athlete. This would be bradycardia. Okay, stroke volume 70 milliliters. Okay, and a trained athlete up to 100 milliliters at rest. And if you haven't already noticed, they're both 5 liters per minute. Okay, so stroke volume 70 milliliters per beat, a trained athlete 100 milliliters per beat. So what's happening here is the trained athlete not having to work as hard. It's just more efficient. It's getting the same liters of blood out per minute as an untrained athlete without having to work as hard. And the reason links back to that cardiac hypertrophy. They have an increase in their cardiac muscle. Okay, so that cardiac muscle is more efficient as a greater volume of blood can be ejected per beat, and therefore their heart rate can reduce. It can just lower because their stroke volume is higher. Okay, and if we were to look at that on a graph, you'll see there, okay, untrained heart rate in the blue, stroke volume in the green. And as you can see, from the untrained to trained, the heart rate's lower. Okay, stroke volume accounts for much more of the cardiac output. And you've got about half and half there between an untrained. Okay, heart rate for half and stroke volume for half. Okay, so there is going to be another video on heart rate, stroke volume and cardiac output where we're going to be looking at the response to exercise and recovery. But I hope this just helps you understand the terms, gives you some resting values, and just gives you an idea of Starling's law and things that stroke volume is dependent on. Thank you.